And now we tackle the all-important topic of self-inductance. So we have a coil, and I'm not going to wrap another coil around this right now. Two potential issues or considerations that you might have picked up on. The first one especially, in the last little lesson, we saw that we had a changing current that produces a changing B field in the coil, this solenoid. And if that B field passes through a separate coil, one wrapped around it, it induces a current in that coil. That's second coil. And then that second coil will produce a changing B field opposing the original changing B field. And that B field induces a current in the original coil, and etc., etc. So in the last little example, we considered the changing current in this one, inducing an EMF in the larger coil. You had a changing current in that one, inducing an EMF back in the original. So that's the first, like conflict or consideration that you probably picked up on. And, it goes back and forth like this. So how do you deal with all that back and forth effect? Well, the bottom line is the mutual inductance takes care of all that. So the mutual inductance that we described handles it all in one fell swoop. So it describes, or it gives the proportionality constant for the effect of the induction effect from one to the other. But there's still a second consideration here, a second tension that you might have felt. This coil that has a changing EMF has a current that produces a changing flux, and it finds itself embedded in that changing flux, its own changing flux. So a changing current produces a changing magnetic flux, inducing an EMF in the coils of itself. And that phenomena is known as self-induction. Self-induction or self-inductance is of more importance than this concept of mutual inductance for our purposes. The symbol is L. Okay, instead of M, it's got its own special symbol. Now, in a coil, the changing flux it produces all passes through itself, right? I mean, come on. It's produced in a B field, and that B field is inside itself. There's a changing flux. And so it follows then that the inductance, the self-inductance, equals N phi B over I. Now, this is affecting itself, not something else. Notice we're not going, well, let's see, the self-induction is, the number of turns in the secondary one times the flux in the secondary one over the current, I should say, the number of turns times the flux in itself divided by the current in the other one. All that is just itself, every one of these quantities, okay? So that makes it easier. For one thing, we don't have to worry about the subscripts, but it has the same form. And here's a very awesome result that emerges from this emergent quality, so to speak. If we multiply by I, so we have Li is N phi B. Now, let's take the time rate of change. L di dt is N d phi sub B dt. Oh, N d phi sub B dt. We know what that is. That is negative EMF induced. Therefore, EMF equals minus L di dt. This is a self-induced EMF. The negative sign is basically the Lenz result, which is always that the induced effect opposes the original change. So this is an inductor or it's a choke. This is a kind of a I don't want to say necessarily slang, but just a common name associated with the function of an inductor, namely that it chokes itself off. If there's a change in current, it induces an EMF to prevent that change. So in that sense, it's a choke to a changing current. Or another way I like to think of it is in a current inertia. So if you want to change the current, there is an inertia that's imposed by the induced EMF, the self-induced EMF, that prevents that change from occurring. according to L d I dt. The faster you try and change the current, the more EMF is induced in itself to prevent that change. And so now let's take a look at how this is going to practically turn out. We have a resistor and inductor. Both these look very similar. AB, AB, we have a current flowing through. Now VAB in a resistor is just IR. It's a drop across there. For the inductor, we have, we'll say, the magnitude of the voltage at least is L d I dt. So now we have a component here that we've used with Kirchhoff, right? IR. That's the voltage. Now we have a voltage across this new component that's L d I dt. And now we need to figure out the direction of the EMF induced in itself. So let's now carefully consider the direction of that self-induced EMF in the inductor. So I'm looking at 3 scenarios. Keep in mind that what we just realized now, this thing is, you can consider this as a current inertia so that it doesn't like change. It's the Lenz's law thing. So anytime a current is changing, it's going to oppose it. So the induced EMF direction follows directly. First scenario, constant current. What's the IDT? Obviously 0. Therefore, if there is no dIdt, then LdIdt is 0. So, nothing. Constant current sits there, no EMF across, no voltage across the inductor. In the second scenario, the current is going up, so we have a dIdt that's not 0. In fact, it's positive. So it's increasing in this direction. Now, the induction effect is going to be such as to oppose that change. So the EMF induced is going to be in this direction, like an electric field in this direction, right? So that means we're going from, we have positive at A compared to B. The EMF is induced in this direction from B to A. That's a rise in potential going across there, more positive at A. And that is the condition that will result in an opposition to this direction of current, which is also the direction it's changing. In the last scenario, we have dIdt is negative. We're reducing the current in this direction. So the EMF induced is going to try and keep that from changing. So it's going to be in the same direction as that current. So it doesn't decrease. It's going to try and keep it from decreasing. So we go from negative to positive, A to B. So there it is. And now let's consider a toroid solenoid, air core. This isn't actually showing an air core, but nevertheless, we see a toroid cross-section A, which would be the cross-sectional area of the coil itself, and then radius R, which is from here to here, closely wound with N turns of wire, and determine its self-inductance. So we just go back to the fundamental idea. B is equal to mu 0 Ni, which is mu 0 big Ni over 2 pi r, turns per length. Now, the self-inductance, N phi sub B over I. Okay, so that's N. Phi B is BA over I, and we know what B is. Consider that each turn contributes to B, so the B field itself is related or proportional to N. So it's N times B, there's B, times A over I. Notice N appears twice. It appears, the inductance, self-inductance is proportional to N, and then the B field itself is proportional to N. So the number of turns really affects this. Well, like with mutual inductance, we had the mutual inductance of 2 coils is proportional to the turns of each one. Same idea here. And so we have that the self-inductance, mu 0 N squared A over 2 pi r. Let's augment our understanding of the coil, the inductor, with the consideration of the energy and energy density of the inductor. So here we have the basic picture. And as the current increases in this coil, as it increases, it produces a increasing magnetic field. That changing or increasing magnetic field produces a changing electric field. It's a non-electrostatic E field, a non-electrostatic E field that's actually pushing against the charges. It's inducing an EMF that opposes the current. It's acting in the opposite direction. Here's the direction. And so in that sense, that non-electrostatic E field is doing negative work. So as negative work is being done, it's adding energy to the inductor. So energy is being added to the inductor. Now let's assume that there's no resistance in this coil at the moment. Now the VAB, the voltage A to B, is equal to LdI/dt. Now I didn't put negative. In general, Faraday says negative LdI/dt, but it's already in the opposite direction of the current, the increasing current. And so it's a double negative, LdI/dt. Now the power of the source that's delivering current, that current is increasing. This is across the source, so it's like, okay, there's V, the voltage, VAB, times the current. That's all it is. VAB times I, and that's then LI/dt. So there's the power being delivered to the inductor. Now the differential potential energy is then just going to be power dt, PDT, power delivered to the object times differential time. And so the power is Li di. So it's just Li di, PDT. Multiply Li di dt by dt, of course. So the potential energy that is being added or delivered, you could say, to the inductor is L, which is a constant integral from 0 to the maximum current, or I should say the current that it has or ends up with, times I dt, this really time-dependent intermediate I. So that gives us a potential energy of 1/2 Li squared. No I, no U. So this is very satisfying in the sense that we see this form of 1/2, mv squared, kx squared, all those things keep showing up again and again. So here it is again, like 1/2 mv squared. L is like the mass, I is like the velocity. So this form shows up once again. So that is the potential energy associated with a current in an inductor. And of course, a current in an inductor really produces a magnetic field. So that's perhaps more fundamentally where the energy is. So now let's consider the energy density. Being consistent with my fixation on toroids as the quintessential example of a magnetic device, because it's really so useful to consider. Well, the density of the magnetic field energy, which is all contained within here, energy per volume. So it's U, the energy we just discussed, over volume, 2 pi r, which is radius, is the radius, times, so 2 pi r obviously would be the circumference. So that times the cross-sectional area of this coil gives you the volume, the spatial volume of the magnetic field. So 1/2 Li squared over 2 pi r A gives us 1/2. There's the inductance, mu 0 n squared A over 2 pi r. Some cancellation gives us 1/2 mu 0 n squared I squared over 2 pi r squared. Now look at this quantity here. Mu 0 n I over 2 pi r is the magnetic field of a solenoid. And all these quantities are, the 2 pi r is squared, the n is squared, the I is squared, only the mu 0 is not. So this is B squared divided by mu 0. So we can write it that way. Mu equals, or U I should say, B squared over 2 mu 0. Mu 0, of course, being the permeability of free space, so it's mu for any particular material. So we see that the energy density really is contained in the B field and obviously highly dependent on it. So that will basically conclude our introduction to the self-inductor, which is the most important part of our consideration of the way in which coils interact with each other, how they interact with themselves, because the next step is going to be to see how we use this inductor in actual circuits using Kirchhoff's laws. So that'll be the next topic.